In the previous videos, we were looking at finding the regions bounded by curves that were defined as functions of x. So what if instead we had a horizontal orientation? What if our curves were defined as functions of y? So something like the image we have here on the page. So if we had x as a function of y and another x as a g of a function of y, so x is f of y and x is g of y, as you see here in the blue and the red graph, and we wanted the area of the region between those curves. How could we do that? Because that is sometimes the way we're going to see curves, and we'll see an example in just a minute. So how could we do that? Well, all we have to do is reorient our Riemann sum a little bit. So let's take a look. So if we had a region and it turned out that our curves were defined as functions of y instead of functions of x, as I have here, what we could do is the same thing we did when we had functions of x. We divided up the interval from a to b. In this case, let's start out here. So let's say let x equal f of y and x equal g of y be continuous functions. Now they're functions of y, but they're continuous functions on the interval. Because they're functions of y, I'm going to write it this way, where y is on the interval from c to d. And I added in that y just to remind us that c and d are on the y-axis, as you can see right here. So let's suppose we're looking at that y-axis from c to d. And if we want the area of the region, one other thing. Just let's also say where f of y is greater than or equal to g of y on that interval from c to d. So it's oriented and it looks like we have here, where f of x is the bigger function. Those x values are larger than the function g of y, the output values there. Okay, so if that were the case, then to find the area of the region, we're just going to follow a couple of quick steps and create that Riemann sum that will give us an integral. So let's think about it. We're going to divide the interval. We're just simply going to divide c to d into n subintervals of width. This time, our width is going to be a delta y. Delta y is going to be d minus c over n. Then we're going to pick a tag on each subinterval. We'll call it x sub I star. On each subinterval, I'm going to call it subint because I'm running towards the end of my screen there. So on each subinterval, x sub I minus 1 to x sub I, and find the area of a rectangle on that interval. Okay, so what would the area of a rectangle on that interval look like? Well, the area of a rectangle is always going to be, so the area of a rectangle is always going to be the width. Let's actually write height first. It's going to be the height times the width. Well, we know what the width of the rectangle is. You can see a little rectangle right here. That width right there is going to be that delta y value. Now remember what we're going to do with that delta y. That delta y is going to get infinitely small so that we can get the actual area, not an approximation of the area. So the area of the rectangle is just going to be the height times the width. Well, what is that going to look like? Well, the height of those rectangles, right? And you almost have to like orient your head sideways. Like you guys can't see me right now because I'm just making this video on the white screen, but on the whiteboard. But this length right here, technically it's oriented that way. I'm calling it height. But, I'm just sort of turning my head and I'm thinking, how do I find that height? Well, I would take this function, which is the bigger function, f of x, and I would subtract the smaller function, g of x. That's going to give me that height of that rectangle. So I'm going to get f of y sub I star minus g of y sub I star. And the width, well, we already talked about the width. The width is delta y. So that's the area of, I'm trying to get this all on the same screen. So that's the area of each of the rectangles. Well, how do we find the area of the total region? Well, this is where Riemann sums come in. So the area of the region bounded by f of y and g of y as we define them above on c to d is going to be equal to the limit. We're going to take n rectangles. We're going to add them all up, and then we're going to let the number of rectangles n go to infinity. So it's going to be the limit as n goes to infinity of the area, the sum of the area of n rectangles. So that's f of y sub I star minus g of y sub I star times delta y. But here's the kicker. That is a Riemann sum, and we know by the definition of the definite integral that that is an integral from c to d of f of y minus g of y dy. Our integral, our differential, because we're going in a vertical orientation here along the y-axis. We're dividing up the y-axis into n subintervals there. So this is going to be the integral with respect to y. These are functions of y, and this is going to be the integral with respect to y. So that is how we find the area. We're going to do one last little notation here before I walk away from this image and this derivation. We're going to say, you know what, just like we did before, we talked about how when f of x is the bigger function than g of x, we called it the function on top and the function on the bottom. Here, because our orientation has changed to a horizontal orientation, we're going to talk about the larger function is going to be the function on the right. And so what we're going to do is we're going to add in some subnotation on these x's, and we're going to call f of x x sub r, the function on the right. So that r stands for right, meaning it's the larger function because it's on, we're thinking of going horizontally. So the values that are bigger will be on the right. And then x sub L is what we're going to call g of y, and that's going to be the function on the left. So we're just going to add one more piece of notation in here. It's sort of shorthand notation. I like this notation when I'm being quick and thinking about orientation. So this is x sub r minus x sub L, the difference between the function on the right and the function on the left, and it's with respect to y. Okay, and we'll freeze that. That's our derivation of our new formula. Now we're going to do a couple examples, but that's the derivation of the new formula. And we could come over here. Now that's the example we're going to do. Let me pause this and find the formula nicely typed up. All right, so here you see the formula nicely typed up. So if we're trying to find the area between two curves, we call, I don't have the picture anymore, but when we've got two curves, we're talking about looking at x sub r. Anytime we've got two curves, let's make it look something like that's kind of fun. X sub r equals f of y, and x sub L equals f, g actually, g of y. Let's scooch that back a little. I'm running into my curve. X sub L equals g of y. And if we want this area of this region right here between, in this case I did intersection points, so in between C and D, if we want the area of a region and it's better to orient it horizontally or to work with it horizontally, then we think of creating rectangles, and we call x bar the function on the right, x sub L the function on the left. Then the integral, the area, is going to be the integral from C to D of f of y minus g of y dy, or shorthand x sub r minus x sub L, the function on the right minus the function on the left. Okay, so what does that look like in practice? Let's take a look. I have little notes right there to myself, but let's take a look at this particular one. So on this one, if we want to find the region bounded by the curves x equals 1/2 y squared minus 3 and x equals y plus 1, let's say I have to graph those. I'll pull in a Desmos graph that's nicer. We can always go to technology to do the graphs, but we also need to know how to graph our regions and find the areas that we're looking for graphically without technology. So let's talk about doing that, this little pre-calc review here. This is just a parabola, but the orientation of this parabola, since it's x equals a y squared, it's a horizontal, so it's going to be opening to the left or to the right. Since the a value in front of the y squared is positive, we know it's opening to the right. The 1/2 is changing how it opens or closes, basically, but you can adjust that with plotting points. The -3 is shifting it backwards 3 units. So that's shifting it backwards 3 units. So we're going to be here is where we're going to be starting at, and we're going to have a graph that opens something like this. And I'm going to kind of just give just a general shape so we can kind of get started working with it. We could plot some more points to get a better idea, but that's the general shape of that parabola, and that gives us a starting place. X equals y plus 1, well, that is a line. That's a linear equation. It's a little harder to graph in this form, x equals y plus 1. We're used to graphing in y equals mx plus b. So if I just solve for y in this case, so if I go ahead and I solve for y here, let's go ahead, that would just be y equals x minus 1. I'm going to solve for y. I also shifted things around. So y equals x minus 1. So that means we have a line with a y-intercept of -1 and a slope of 1. So our line is going to go up here. This is going to go this way. We'll find those intersection points here in just a second. But we get that general shape. Now, that might not be exact, and we might not have the right intersection points on the graph because we really just were eyeballing it. But that is the region of the graph that I want to find. But what I want to do first is I want to actually figure out what those intersection points are, because that'll give me a better scale here. So let's find the intersection points. So to find intersection points, we're going to set these two curves equal to each other. So I'm going to go ahead and shift back over to black. So let's go ahead and set those two curves equal to each other to find the intersection points. That's always how we find intersection points. So 1/2 y squared minus 3 equals y plus 1. Playing around a little bit with that, I'm going to move all the terms to one side. 1/2 y squared minus y minus 4 equals 0. And then I'm going to go ahead and just do a little fraction busting. If I multiply everything here by 2, I'll make it easier to work with without the fractions. I get y squared minus 2y minus 8 equals 0. That's now a quadratic, and I can factor it. So I get y minus 4 and y plus 2 equals 0. So y equals 4 and y equals -2. So those are my bounds on the y-axis. Those are, and again, my scale might not be right here, right? Because I was just kind of eyeballing, but I can get a generalization here. So this should be -2 right here, -2. Okay, so my scale might not be perfect, but we get a good idea. We can find the x values really quickly too by just plugging those back if we wanted those as actual ordered pairs. So if y equals 4, then x would be 5. I'm plugging them back into this guy real quick. When y is -2, then x is -1. So our intersection points are actually at 5, 4, and -1, -2. So that's what those 2 points right there. This is at 5, 4, and this is at -1, -2. Okay, so we found the region. We have a nice graph, or a decent enough graph. I have a nicer graph right here. I'm going to go ahead and just drag that in. To scale that I pulled in from Desmos, and we can see like we did a pretty good job of getting our graph, and we did it pretty quickly using some algebra and a couple pieces of algebra, thinking about parabolas, lines, and intersection points. Okay, so if that is our graph, so there's the graph that this is the area that I want to find, and what I want to say is now we have to decide how we're going to set this up. So it is fairly clear to me at the very beginning here that this was, because this was defined as a function of y, x is a function of y, as was this one. This was x was a function of y. To graph it, we turned it into y as a function of x as well. But it's fairly clear to me here that we want to use a horizontal orientation. But let me show you one other reason why we would want to use a horizontal orientation. If instead we wanted to use a vertical orientation, right? So we wanted to find the area of this region, we'd have to be a little bit creative, because take a look. We would actually have to split this up. We'd have to break this up. Notice, because in order to do a vertical orientation, right, we have to figure out which function's on top and which function's on bottom. And that is not as easy vertically, because we'd have to actually split this part up. Let me grab my highlighter. We'd have to split this parabola up into 2 pieces, because remember, x was equal to 1/2 y squared minus 3. So if I wanted to solve for y, I would have to get 2x plus 6 equals y squared. I'd have to take the square root, which gives me 2 functions. So y is the positive square root of 2x plus 6, and y is the negative square root of 2x plus 6, ... right? We have 2 functions. We have this root on top and then we have the root on the bottom. And in order to use our area formula for functions of x, we have to split this up. We'd have to figure out, okay, well, my rectangle's built from -3 up to -1, this region right here. In that region right there, my rectangles, their top function is the positive square root and the bottom function is the negative square root. But then my region switches. Now on this next region, starting from -1 all the way out to 5, see my rectangles in there, the function on the top on that region is the positive square root and the bottom is the line. And so I look at that and I think, you know what? This is going to be easier to do if we use our horizontal orientation, because throughout the region, if I think of drawing my rectangles, throughout the whole interval on the y-axis, which on the y-axis, remember, we're running from -2 to +4. On that whole region, when I draw my rectangles, and I've drawn a few of my representative rectangles right there, the function on the right is the line, and the line is y plus 1. And the function on the left is the parabola for all of those rectangles. Every time I build those rectangles, when I compute the height, and again, you kind of have to think of height like you're kind of twisting your head a little bit to the side to look at that. But the function on the right is that line, and the function on the left is that parabola, which is 1/2 y squared minus 3. And we can use our new formula that we've just derived to calculate the area by adding up those rectangles, taking the limit as n goes to infinity, which gives us an integral. We can use that with respect to y, and that just makes more sense in this scenario. Could we do it the other way? Of course. It's just going to take more work, and we want to be efficient. So I'm going to get rid of this right here because it doesn't make sense for us to try to rewrite that function, because we can work with it as a function of y. So how am I going to compute the area? Well, let's get it set up. So the area is going to be equal to the integral. I'm going to be calculating areas of rectangles from -2 to 4, or slicing this region up. That's another way I'll say that. From -2 to 4, I need to take, we've already talked about it, I need to take the function on the right minus the function on the left, and I'm going to be integrating with respect to y, because it's easier in this case to go with respect to y. So that area is going to be -2 to 4. The function on the right is the line, y plus 1, and we're going to subtract the function on the left, which is 1/2 y squared minus 3, and we're going to integrate with respect to y. Now I'm going to zoom out and I'm going to pause the video. That's a fairly simple integral to calculate, just our basic integration strategies. So I'm going to go ahead and pause the video. I'm going to do that, and then we'll come back once we have the answer. Okay, and there we have it. 18 units squared of area. So let's zoom out so we can get that whole situation, get that whole example, both graphs and everything. The graph we created, the graph from Desmos, the setup, finding the function on the right minus the function on the left, all the way through the calculation of the integral to the value of 18 square units of area. 18 units squared of area is enclosed between those two graphs. All right, and so that is how we set it up if we want to do it horizontally. So now we are able to do both vertical and horizontal orientations for finding regions of graphs and determining the bounds by the functions.